Hi everyone, Mr. Boltri here bringing you video 2.6 in which we're going to talk about what happens when we're allowed to change directions. So up until this point, we've only been moving in one direction at a time, either the positive direction or the negative direction. And there's been some interesting problems with that, but hopefully you'll notice that when we are able to change directions, either move in the positive direction and then the negative direction or vice versa, things get even more interesting. So in order to talk about this, I have prepared a special example for you. So I have this little car that it was starting at a position of 0, which you can tell because I put the little cone down. And then it is going to drive to the right. Actually, let's just watch it and then we'll talk about it. So it is going to drive to the right and it's going to go pretty slow. And then it hits the boxes and it stops. And then it zooms out of there. Maybe it's just trying to leave the scene. Let's watch it again. And you'll notice that as it's driving, it's a little bit slow at the beginning, and it kind of is jerky as it goes slow. It prefers to go fast, but we're just kind of gloss over that and smooth over that and say that at the beginning, we're going to pretend like this is just a nice constant velocity, but a slow constant velocity. And then it stops, and then it moves very fast to the left, so in the negative direction. So what I'm going to ask that you do is try to make the position versus time graph associated with that motion. So we're going to watch it one more time, and then I'll ask that you draw the position versus time graph in your lab notebook. And at any point, please feel free to pause the video if you need more time, or rewind the video if you need to see something again before I reveal the answers to you. So to help you make the position versus time graph, let's watch it one more time. Again, the starting position is 0, and then it's going to move to the right at a slow, constant velocity. We're going to kind of gloss over this and say constant velocity, but slow. And then it hits the wall and stops, and then zooms as fast as it can all the way to the left. So using that information, try now, and you might need to pause the video to give yourself more time, to make the best representation that you can of the position versus time graph for that little car. So when I made the position versus time graph, it looked a little bit something like this. So it's moving in the positive direction, but not very fast, which you can tell because the slope is not very steep. And then it stops, which you can tell because the slope is 0, so the velocity is 0. And then it moves in the negative direction very fast, which you can tell because the slope is rather steep. I actually could have made this even more shallow and more steep just to sort of like highlight the difference. But I'm hoping that you can see the patterns here, and that's slow to the right, stopped, and fast to the left. So based on this position versus time graph, now let's also try to make the velocity versus time graph. So you might need to pause the video again and just try to figure out, well, what is this positive, what is this part of the position versus time graph going to look like when we translate it to the VT graph, and this part and this part. So do all three parts now. So when I did it, I got something that looked a little bit like this, with a small positive velocity, a velocity of 0 for a period of time, and then a big negative velocity for a shorter period of time. So yeah, this is kind of what it looks like when we have a position versus time and a velocity versus time graph with different velocities. But the only thing that I do want to point out here is that it did hit the wall. So we kind of want to show that the velocity went from a positive number down to 0, and then went from 0 down to a big negative number. So we're just going to use this dashed line to show that the velocity changed from here to here and here to here. It just sort of like cleans up the graph and makes it easier to look at. And also, obviously, we know that it had to go from 0 to a big negative number. So this just shows that the velocity is changing from 0 to that big negative velocity. So I'm going to ask that you, when you're making velocity versus time graphs, include that dashed line. If nothing else, it just sort of helps us to keep track of what is the velocity at different times to make sure that we only have one velocity at a time and we never have any overlap of our velocities. So in order to continue our conversation about this, I actually do need to clarify one thing, because I've been talking about velocity as if it's one thing, but it's actually, there's two different kinds or flavors of velocity. In the same way that we have a time interval and a clock reading, we have also two different kinds of velocity. So I'm going to ask that you write both of these definitions and the new vocabulary words down in your lab notebook. The first is going to be instantaneous velocity, which, as the name suggests, is the velocity at a single instant or clock reading or a moment in time. So let's call this 1 second. What is the velocity right there, boom, at 1 second? As opposed to an average velocity, which is if you take a bunch of instantaneous velocities, here we have, I'm just going to make up numbers. Let's call this 2 tiles per second, 2 tiles per second, 2 tiles per second, 0 tiles per second, 0, and then -5, -5. We take all those instantaneous velocities and we average them out. Then that gives us the average velocity, which is the one sort of overall average velocity value that represents the cumulative average of all the individual instantaneous velocities over a given time interval. So you'll notice that instantaneous velocity has to do with a clock reading and average velocity has to do with a time interval. And you'll notice that the same thing is true of like position and displacement. Position is at a clock reading and displacement is over a time interval. So make sure to get both of these definitions down. And up until this point, we've only been talking about instantaneous velocity because we've never had velocity that's changed. So our instantaneous velocity has always equaled our average velocity because we've only ever had one at a time. But now that we have multiple different instantaneous velocities at different times, we are going to need to start thinking about how we can find the average velocity. But before we get too deep into it, we also have to remember that the same thing can be said about speed. Or not remember, I need to tell you that the same thing can be said about speed. So you'll notice that all of these definitions are exactly identical, except for everywhere you see the word velocity, you can replace it with the word speed. So make sure you get all 4 of these definitions down, but maybe you can shorten these definitions because they're literally exactly the same as the instantaneous and average velocity, except just everywhere you see the word velocity, we're replacing it with speed. Because instantaneous speed is associated with a single clock reading or an instant or a moment in time, and average speed is the cumulative of a bunch of instantaneous speeds over a time interval. So in our next class, our objective is going to be try to figure out how we can use these graphs to determine or calculate the average velocity and the average speed. So what I'm going to leave you with in this video is a question. So using these graphs, how would you try to figure out, let's assume that I gave you numbers, how would you try to use those numbers to calculate the average velocity? Well, so this is going to be some positive number, so and then it's going to be some zeros, and then it's going to be a big negative number. So if we average all of these out, what would we say would be kind of the average of all of those velocities? And then when we're finding the average speed, remember speed, we don't really care about direction. So this is going to be a small positive number, 0, and then a big positive number. So how would we average all of those out too? So I want you to start thinking about how could you find, using these graphs or numbers, depends on what I give you in the problem, but in our next class, we're going to focus on the position versus time and the velocity versus time graphs. How can we use those to calculate average velocity and average speed? So I'm looking forward to doing that with you in our next class. I'm looking forward to seeing how you address that problem. But for now, this is Mr. Boltri wrapping up video 2.6, where we did our first introduction into what happens when we're allowed to change directions, specifically looking at what it looks like in a position versus time graph and a velocity versus time graph. I'll see you in our next class. Make sure you let me know if you have any questions, and go Bears.